Hello students, we are starting chapter 4, and in this chapter you guys are going to cover cycloalkanes. So these make up a lot of the natural products in the world, a lot of the compounds in your body, including steroids, cholesterol, and others. So the other thing we're going to do is learn how to draw a chair structure for a six-membered ring. This is a very important thing for you to do, and it may take some practice, but just keep practicing and you'll get it. Okay, so cycloalkanes, there are going to be ring systems with a different number of carbons around the ring. Here I show estrogen. Again, these ring systems make up a lot of compounds in the body. The first few ring systems are shown here. They're given the prefix cyclo and then the prefix for the number of carbons in that ring. So a three-membered ring is cyclopropane, cyclobutane, etc. When you start getting double bonds, you can use the ENE ending, such as cyclopentane if there was a double bond. A little bit of naming, it's very similar to how we did the straight chain. First of all, you want to find the parent. Sometimes the parent is the ring. Sometimes the parent is still a long chain, depending on what you have. If the ring has the same or more carbons, that is the parent. Then you're going to number the substituents as usual. And in general, number, so the sum of the numbers is the lowest possible numbers. So let me just show you this. I'm going to start here at 1, and I'm going to go around the ring so the second substituent methyl here has a 3, as opposed to the other way around the ring to give a 1, 5. The other thing is I could have numbered 1 here with a methyl, but you're going to choose, if you have a choice, if 2 or more substituents can have the same number, different substituents can have the same number, prioritize them alphabetically. So ethyl comes before methyl, and so we give 1, 3 numbering, so 1 ethyl, 3 methyl cyclohexane. In this case, 1 bromo, 2 methyl cyclopentane. Pause this and practice naming these. You should have come up with 1,1 for trimethyl cycloheptane. Any other numbering would have given a higher sum. For example, don't start 1 here, because then you would have had 1, 4, 4 trimethyl. For the right compound, it's 1, 2 dibromo 4 methyl cyclopentane. For the rings, these are locked into place, so they don't have the free rotation around their sigma bonds unless you break the ring. So substituents are locked in place. These result in different compounds with different properties. For example, if I look at a cyclopentane ring and I have 2 methyl groups at the 1 and 2 position, they can be both in the up position, shown here with the wedges, or one could be up and one could be down, shown with a wedge and a dash. These are different compounds. The first one on the same side of the plane of the ring, we say that's cis, and they're either both up or both down. If you flip the molecule over, these all rotate in space, and both down is the same. Or one up, one down, it's trans. We're going to look at a couple ring systems, starting with cyclopropane, and we're going to take a look at the sort of strain that's in these rings. Cyclopropane has something called ring strain, as well as angle strain. So ring strain is due to torsional strain. This is what we talked about in terms of eclipsing atoms. The other thing that it has is angle strain, which is a deviation from the normal sp3 109.5 degree angle. So here, when you just have a normal bond, CCC bond angle, you can open it up. 109.5 is preferred. It's that tetrahedral arrangement. But when you lock these into a ring, you deviate. And cyclopropane has the worst ring strain. Here, it has a 90-degree bond angle. Here in cyclobutane, I'm sorry, I think I said 90. I meant 60-degree bond angle here. That's the worst. Cyclobutane has a 90-degree bond angle. These deviate quite a bit from the normal 109.5, but obviously cyclopropane is more offensive. When you look at ring strain in terms of kcals per mole, you can see that cyclopropane is the highest. Cyclobutane is quite bad as well. As you open it up more, you relieve some of that ring strain, only 7 kcals per mole for cyclopentane. Cyclohexane, 0 ring strain, and getting still quite low with the 7-membered ring. So if I just focus on cyclopropane, I already talked about the ring strain due to angle strain here. But the other thing that's a problem is that it's very rigid and planar because these 3 carbons are locked into place. So that forces these hydrogens to be eclipsed. If you look at a Newman projection down one of the CC bonds, you can see these are eclipsed. You can't really pucker this ring to relieve that. So we also have torsional strain here. There's bending of the bonds because of this 3-membered ring giving this 60-degree angle. So you don't have this direct head-to-head overlap. So overall, more strain can open up more easily than some other ring systems. Cyclobutane and cyclopentane allow for some puckering of the rings, so it's not planar. So you can minimize that eclipsing H. So if you look down the Newman projection and see for cyclopentane, you have a more staggered arrangement instead of an eclipsed arrangement. Also, once you get to cyclopentane, you can adopt something closer to the tetrahedral 109 degree. You can get to 108 degrees. Cyclohexane is one of the most ubiquitous, and you have no strain, no ring strain, 0 kcals per mole, and the angles that you can achieve are 109 degrees. There's also no torsional strain because the hydrogens are staggered. So we can look at, and I'm going to show here, a 6-membered ring. So if you want, you could pull out your models. You'll definitely need your models for the next video, but you can join 6 carbons in a ring. I put alternating white balls as hydrogens to show that these are what's called equatorial, towards the equator or flat away from the ring. And the ones straight up and down, I took the balls off so you could see it more clearly. What we'll see in the next video is you guys can do a ring flip. Those that are straight up and down axial will become equatorial, and those equatorial become axial, straight up and down. So I'm going to show that more next time. But basically, if you look down, this carbon-carbon bond here, say 1 and 6, and 3 and 4, you can have 2 different Newman projections, and you can see that these are all staggered. Shown here. That's why there is no strain. This sort of chair conformation is the preferred conformation. We'll look at a couple others. There's a boat, that's the next main conformation, and you can see we get chair and boat from these little depictions here. And the boat is just simply taking the chair. You see how there's a top end where this lady's head is sitting on her chaise lounge, and her feet, you basically pull the feet up, that gives you the boat, shown here. Okay, the main thing is that boat is higher in energy than the chair structures. And you have to go through some half chairs, twists. I don't need you to know that. But boat is higher in energy because these top guys bump into each other. and you guys will be working in your labs playing around with model sets, and you can do that now. You can see that there's a hydrogen here and here bumping into each other. So this is less preferred, but to go between chair and boat, and to go between chair structures, you have to go through the boat. The energetic barrier is 11 kcals per mole, which is actually rapid at room temperature. So you're constantly doing this sort of chair flip. The last thing we're going to talk about in this video is how to draw a chair structure. This is important for you to do because you'll have to draw these for some homeworks, for some exams. You'll draw 2 parallel lines first. Notice they're not straight up and down. Then 2 other parallel lines. And notice these are at a 90-degree angle. Then complete with these lines here to give your 6-membered ring. Then when you want to draw the equatorial bonds that go out to the sides, these are always parallel to 2 bonds over. So you could do 2 parallel here, then 2 that are parallel to this bond and parallel out here, then these last 2 here. So right there you have all of your equatorial bonds. Notice that every other one is one's going up, one's pointed down, one's pointed up, one's pointed down. We'll see that same pattern with axial. We're going to draw the axial bonds, and these go straight up and down. You could do the first 3 straight down, and it's every other carbon you go straight down, then straight up. Then you could draw all the ones straight up, and you could see straight down, straight up, straight down, straight up. This is important for you to not only work with your models, but also to note if something's axial or equatorial, and also to be able to note if they're up or down. There are 2 different distinctions. One, you're going to find that equatorials are lower in energy because they're pointed away from this ring area. And then separately, the up or down distinction will help you with defining something as cis or trans. Okay, in our next video, we're going to go through different conformations, so please have your models ready.